based on that. Oh, I wanted to say one more thing about this. So the Earth's orbit is not a perfect circle, as you can see in this diagram. Now, this diagram greatly exaggerates how elliptical the Earth's orbit actually is, but I wanted to point this out because we'll talk about it later. So the eccentricity of an orbit tells you how flat that ellipse is. And the eccentricity goes from 0 for a perfect circle up to 1 for a really flat or pancake shape. And the Earth's eccentricity is 0.0167, so very slightly eccentric. And most of the planets in our solar system are almost circular, with sort of the notable exception of Mercury, which is at 0.2, and Pluto as well at 0.2, and Mars at 0.1. Okay, and then combine those two motions with the fact that the Earth is tilted, and you can explain a whole bunch of different phenomena that you see during the course of the year. So the Earth's rotation axis isn't perpendicular to its orbital plane. It's tilted by 23.5 degrees. That's called the obliquity of the ecliptic. And that can explain the seasons, right? So during certain times of the year, if this is the sun, we're pointed more towards the sun and we'll have a longer day, whereas if we're over here, we're pointed away from the sun and we'll have shorter days during those times of the year. The moon's orbit is its own thing here, but the moon and the Earth both rotate or revolve around the sun, and as the Earth and the moon go around the sun, the moon also orbits the Earth, and so it traces out this S-shaped pattern as it goes around. And this can, of course, explain the phases of the moon, that during certain times, or certain positions of the moon's orbit, I'll see different parts of its face lit up. So, for example, when the moon, so the sun is up here at the top of the board, right? And so when the moon here is in its orbit and it's up here, that lit half of the moon is facing away from us, and so we won't be able to see any of it. And the moon will be dark, and we call that a new moon. Whereas over here, all of the moon's face is lit up, and we can see it, and that's called a full moon. Okay. So moving on to the solar system. We have 4 inner planets that are rocky, and 4 outer planets which are large gas giants. So the outer planets, the gas giants, if you went there, you couldn't actually stand on the surface. You would just sink into the gas. So they don't have a nice rocky surface where you can stand on, and that's where they get the name gas giants. And even further out from those planets, we have a whole bunch of what we call dwarf planets. So you might object to the fact that Pluto has been downgraded from a planet to a dwarf planet, but it actually makes sense because there are a whole bunch of these objects that are around the same size and at about the same distance from the sun as Pluto, and it makes sense to group Pluto with those objects rather than with the rest of the planets. But if you still want to call it a planet, I won't dock you any points, right? So. And if you think about the solar system, the sun, I think about it like a symphony, and the sun is the conductor. He's the one that's telling everybody what to do. He's definitely in charge. And then Jupiter is the loudest in the symphony. So maybe like a really annoying trumpet or an entire horn section that's outplaying everybody else in the whole symphony. And the other planets make up the other different instruments or sections of the orchestra. And then we have a whole bunch of small objects. We have asteroids and comets, and there are very many of those, but they're very small. So maybe they add only a small voice to the symphony, like the voices in the choir. And then we also have the solar wind, which is the sun is emitting particles out into space. And all this adds to the, harmony or disharmony of the solar system. And the sun is the conductor, and he conducts with one simple rule. And that's Newton's universal law of gravitation. And the rule works as follows. So I find that I'm really attracted to this man in the front row here. And it seems that the closer I get to him, the more attracted I am. But unfortunately, he's attracted to everybody else in the room. And so am I. So I don't know how that's going to work. Well, anyway, this explains, it's a silly joke. And I noticed nobody laughed, so thank you for that. But it explains the law of gravitation, that every mass is attracted to all the other masses, and the way that it works is as follows. I have the the equation up here, but basically the larger the masses are, the larger the force is. And then it goes as the distance between, 1 over the distance between them squared. And that means the further the masses are from each other, the smaller the force that they feel. And it isn't just the fact that if the two masses are twice as far away, they feel half the force. They actually feel 1/4 of the force because of that square term at the bottom. So if they're 3 times further away, they feel 1/9 of the force. And here's Newton sitting on his chair, and of course an apple is attracted to his head, but also attracted to the earth as a whole. And this rule is absolute. It's called universal for a reason. It's absolute and it's unbreakable, but that doesn't mean that it isn't uninteresting. Okay, so each planet, to take a look at why this rule, from one simple rule we can build up a multitude of complexities. I want to take an example, or look at an example of the sun and how each planet influences the sun. So if I want to take a look at the center of mass of the solar system, or I think about the center of mass between the sun and the earth, and I want to know how that center of mass changes. The center of mass is like a balance point. So here I have 2 people on a teeter-totter, and one is very large, because the sun is very large compared to the earth. The earth is very small compared to the sun, and if you wanted to balance 2 people like that, so say you wanted to balance Hagrid, it's a very large person, and you wanted to balance him with the baby Harry Potter, on the other end of the teeter-totter, well, where does Hagrid have to sit in order not to launch the baby? Right? He has to sit really close to the fulcrum. And if you've ever ridden a teeter-totter with a young child, clearly nobody has. He has to sit really close to the fulcrum in order to balance. And so the center of mass of the solar system, because the other planets are so small compared to the sun, so Jupiter is only 1/1000th of the mass of the sun, and everything else is much smaller than that even. The center of mass of the solar system at times is pretty much inside of the sun, but at times can wander just outside of the solar radius. So think about how a planet, when it moves around the sun, will influence the motion of the sun around its center of mass. It's going to cause it to wiggle a little bit. And each planet is going to influence this wiggle. And if I add all the planets together, I get this yellow curve here, which shows how the sun moves with respect to the center of mass, or how the center of mass of the solar system is moving. So if I wanted to get at more intricacies of the motion, I might subtract out Jupiter, pretend Jupiter didn't exist and subtract it out. And this is what the motion looks like. Okay, so it seems like the majority of the motion is due to Jupiter, and we expected that. But now let's subtract out all the giant planets. And now I've had to zoom in quite a bit. So I was at 1,300,000 kilometers here, and now I had to zoom in to only 870 kilometers to capture this motion. The motion of the Earth causes the majority of this wobble, and so forth. So each planet has an influence, not only on the sun in this example, but each planet influences all the other planets as well as they go around. And these influences can cause rich dynamical behavior. And even small changes are important. So if you remember the earthquake that went on, or that happened in Chile of this year, it was magnitude 8.8, which if you know anything about earthquakes is a big one. And now, because of that earthquake, changing the mass distribution of the Earth, the days are shorter by 1.26 microseconds. So a microsecond is a millionth of a second, very small. And the figure axis, so that's the axis about which the Earth's mass is centered, shifted by 8 centimeters. 8 centimeters, about that big, so not very much compared to the radius of the Earth, which is about 6,300 kilometers, but still, these small changes can and do have effects on any orbiting bodies around the Earth.